What I want to do now is I want to start going more into the specifics of your site. Okay, so what we've been talking about up till now is basically just Hitec in general. How it works in general, how it works from one site to another. But now we're going to get into more of specifics of how it's designed special for your site. Okay, because no two sites are the same. They're always different in how they're designed, whether it be voltage configuration, the auxiliaries that are used, whether it's in a container or in a separate room such as what you have it. So let's start hitting on site specifics of this particular site, and we'll start that by looking at the general one line of what you have here for U of W. All right, so this is your basic Hitec one line looking at the input and the output. Okay, and what I've done is I've taken the different panels that you have and I've kind of outlined them in red. So the red indicates a separate panel outside of the medium voltage switchgear. Everything else that's not in red is basically following the one line as it exists in the medium voltage switchgear, okay, which is that 5 or 6 section of medium voltage gear that sits on the opposite side of the UCP, which is 4160 switchgear. Has a very nice, arc flash resistant design to it. It's very, very robust and stout. But anything outside of the red box basically pertains to the medium voltage switchgear. Okay, so what we've got here coming in, we've got our utility coming in. We've got basically an input bus here. Here's our Q1 breaker. And then we come through, this is our choke, which is external to the switchgear, so it's in red. So we've got basically a cable connection from this point to our choke to the input of the choke. We've got a cable connection from the output of the choke going back into the switchgear, back into the line side of Q2. So that's our Q2 output breaker. And then we've got our bypass that basically bypasses around the system with our Q3 breaker. We've got basically a output bus here. And then we've also got what we call tapped off of the line side of Q2 is we've got another breaker called Q20, which is feeding a transformer here called the GDP, and then that further will feed into what we call our ADP. And I'll go over all these acronyms here in a second because Hitec uses a lot of acronyms. You'll get familiar with them eventually, okay? But I just want to go through a little bit about this one line here in some detail, and then I'll kind of hit the individual panels as well. And then what we're going to do is probably after this section, we'll actually go downstairs and I'll take you around and kind of show you all these panels and give you kind of a walk around of the unit itself. So if you look at the one line here, again, looking at the utility coming in, this is where our sensing takes place for the utility voltage and frequency. This is all 4160 bus here, so in order to take the signal into our system, we have to knock that down to 120. So you'll have some PTs from 4160 to 120 that knock down that signal so that we can monitor the mains frequency and voltage at a 120 volt level that goes into our DICON, as I mentioned. So that's what this is doing here. We do have a tapping off of here into another transformer. This is about a 45 kVA transformer from 4160 to 480 because there are certain 480 volt loads that we're going to need that will be used by our system that are fed from the utility, basically for starting. Also our preheat system that we use to preheat the diesel comes from this feed, because that's utility feed. We don't need the output feed for preheating, because at that point the diesel is running. So we only need preheating when the utility is available, so therefore we can just use a utility feed for preheat and pre-lube as well. So we take some of that power from this side off of this small transformer, which is built into the switchgear. It's in that first section on the left side is that 45 kVA transformer. Mentioned the Q1 breaker. You can see the CTs that we've got there for both monitoring and for protection. And then, of course, we've got the Q2 breaker, its CTs, the Q3 breaker, its protection CTs. We're monitoring the output voltage here for metering. And then, again, we've got some sensing here going on for the voltage on this side of Q2 and also for the voltage on the output bus. So, again, we need PTs to knock that down to 120 to take into our DICOM. And then the Q20, as I mentioned, is going to be feeding what we call our GTP. Now, this is all, again, 4160 medium voltage. We have a lot of 48 volt loads that we need to supply for our system for our auxiliaries. For example, the radiator works off of 480 volts, three-phase. Our RSP is a 480 volt panel. Our UCP basically requires 480 volts as well to operate. So we have a lot of low voltage 480 volt loads, and that's why we need a GDP, so that we can get some voltage to our low voltage auxiliaries, and they're fed by our ADP, which stands for Auxiliary Distribution Panel. So that's our low voltage 480 volt three-phase panel that is going to feed our auxiliaries. And of course, we want that to be sourced from the critical output, so that that source never goes away. So that becomes a critical source that is fed by the output of our system. That is not included in your rating of the system. In other words, the rating of the system, what you can put on the system at your output, is 1955. This does not detract from that. So we've already accounted for these loads that we need to run our system. It doesn't take away from your load rating on the output. GDP stands for Generator Transformer Panel. So again, that's just the transformer that feeds the ADP for the low voltage loads. And then we have our URP, which again is our choke. URP stands for Unit Reactor Panel. And that's going to feed through the tapping through a GDP, which is our Generator Disconnect Panel, which is simply just a disconnect between the generator output and the choke. Okay, so you can actually open that GDP if need be when the system is down. If you want to, power down the system, make sure there's no voltage on the choke, for example. But that's the GDP, and again, it's just more or less a disconnect, but it's got some CTs on it for measuring purposes, for current measurement, and so forth. It's also actually a fused disconnect, so it does offer some protection should it need to have an overcurrent condition that will blow those fuses. So it does provide some protection as well. Then, of course, you come from that into our junction box of our generator. This is all medium voltage, of course, and so that's the feed into our generator junction box for the alternator. Obviously directional for either operating as a motor or a generator. And then we also have an LRG system, which basically the neutral of the alternator is connected through a resistance ground, and that was provided by Stanley, I think, or McKinstry provided this. That's just basically providing you an LRG system in case you would have a ground fault of some sort, to enable the system to protect against those. Yes?
On the GDP, have we come up with any resolution on the grounding block?
Yeah. The question is, there was a situation with the GDP where it was delivered with a grounding switch. So When you open the disconnect, it actually will ground the feeds coming from the alternator. And that may not be unusual for a genset application. It's a safety way of preventing any stray voltage to accumulate and perhaps discharge itself through an unsafe means. But the problem with that is that if you were to, for whatever reason, open the disconnect while the system is powered up, then that's something that's going to cause an unsafe condition, because you'll have then be grounding a working generator.
For a wide load, that would be fine, but for a wide line.
Yeah, correct. So that's not something that's desirable. Those grounding blades were supposed to have been removed, but for whatever reason they weren't. So what we're going to do is we're going to remove those and therefore eliminate that unsafe condition. Now, you should never be opening the disconnect under power anyway, and you never want to do that anyway, but on chance that you did do that, that would be an unsafe condition. So we're gonna eliminate that altogether. Okay, so again, everything in red is an external panel, and everything else is part of the medium voltage gear. You also have control panels that were delivered with the Hitec system. The UCP, for example, is our main control panel, and it has feeds coming to it, again, from sensing going to the dicon, from the input and the output, and it's got power that comes to it through both the main side, through this transformer, and through the utility side, through the ADP as well. So it has both utility and critical feeds coming into the UCP. The UCP is another panel. As I mentioned, that the UCP is what basically controls the flywheel. And the UCP is also fed from the ADP as well. So it's a low voltage panel. So for example, the power that is given to the pony motor to charge the flywheel comes from the ADP feed into the USP. And I talked about the RSP panel as well, which is the 24-volt starting system for the diesel. It is also fed from the ADP on the low voltage auxiliary side. And having said that, let me go to the ADP one line here. Okay, so this is a deeper look into our ADP. So this is the GDP output, the low voltage three-phase 480 volt output of the GDP coming into our ADP. And so you can see some of the loads that the ADP provides for. This comes into the UCP for three-phase 480 for operating the UCP. Here's the USP feed for 480 volts into the USP. Here's a feed for the fuel system. We delivered a day tank with a day tank control panel that is basically fed from this feed here. There's actually another transformer that knocks it down to 120. So the fuel control panel on the day tank itself is a 120 panel. So there's a transformer in the ADP that knocks this down to 120 that goes into the fuel control panel. We've got a feed into our radiator. So our radiator is fed by a 480 volt three-phase out of the ADP for the radiator motor. And then we've got a couple spares. Also our DCP. Let me go back to that. We've also got some sources, some feeds into what we call the ventilation control panel. So there are a couple of ventilation fans that basically keep the air flowing over the unit. And so we provide the 40 volts for those fans as well. Okay, so that's coming from those two feeds. Back to the DCP. We have a DCP panel that we utilize for medium voltage switchgear. The switchgear itself and the controls for the breakers the switchgear controls that actually send voltage to the breakers to open and close them for the opening, for the trip coils and for the closing coils. That's 125 volt DC power that is utilized to operate those breakers. Our PLC will basically initiate 24 volt control voltage to certain relays, which then will close or open, which will port 125 volt DC for the coils to operate the breakers, to open and close them. But the 125 volt DC that is utilized to operate the breakers comes from a DC panel which contains station batteries so that we can operate the breakers. And these station batteries contain dual rectifiers which are fed by the ADP and by the UCP. This is the ADP feed to the DC panel to one set of rectifiers for keeping those station batteries charged. And then there's another feed coming from our USP. So it's a redundant rectifier feed into the DCP that maintains those station batteries, which are used to provide control voltage, 125 volt DC, to actually control the breakers themselves.
What's the lifespan of those?
Of the batteries? Yeah. I couldn't tell you. I'd have to go check the manual of the DCP. But I think they're just typical NiCad, I believe.
So 3 to 5 years.
Yeah, probably. Okay, so that's what the DCP is, and I'll point that out to you as well when we take our walkthrough. Okay. Let's see. Let's take a deeper dive into the fuel system here. Okay. One of the auxiliaries that we provided for the system, this is a diesel auxiliary, of course, is the fuel system. We have to get fuel to the diesel. And so what we did is we provided a day tank that basically is going to be supplying the engine. Now the day tank is a raised day tank. It's gravity fed. There's a gravity feed of fuel to the engine via the raised tank. And this is another method that we use to ensure a start of the diesel, because we want to make sure that we don't lose prime. So there's always some fuel pressure because of the raised tank coming into the engine. So we've got basically a feed from the day tank through a drop tube coming out and providing gravity feed into the engine itself. So there's always fuel here. It's always ready to go. It's not going to lose prime. We do run it through a fuel filter water separator on the way to the engine. We actually have 2 pre-filters, in fact. One of them is actually on the engine itself, attached to the frame just in front of the engine. The other fuel filter water separator has not been delivered yet. So as soon as it arrives, it'll be placed in line as well. The system is perfectly fine with the pre-filter that it has now. This is a redundant fuel filter that we put on our systems, and once it arrives, it'll be put in as well. It had some supply chain issues with that particular filter. The engine also has its own engine fuel filter, so you're going to have filtration in triplicate once it's all said and done. The day tank, of course, there's going to be a return of fuel from the engine back into the day tank. We take that through a fuel cooler because we don't want the day tank to heat up with any return fuel. We want to make sure that the fuel remains low enough. Yes?
So the day tank's actually siphon fed from the top.
Correct.
Why is that? I don't understand.
Well, and the question is, why is the fuel tank siphoned, out the top through a drop tube? The reason for that is a UL 142 tank cannot have a bottom penetration. It has to have a top penetration. So we can't take the feed off the bottom of the tank.
I understand, because it's a tank.
It's a UL in fraction.
So when we have to change those filters or whatever, then we have to reprime it,
Typically, yeah, when you change the filters, you don't necessarily have to reprime it, but you want to go ahead and run the engine and then let it run a little bit so that it gets all that air out of the system that it might be in it. The gravity feed that will come into it once you're done changing out the filter is going to be enough to maintain your ability to start the engine, but there might be a little bit of air in there that you'll want to run the engine for a few minutes in diesel test mode, for example, or in idle mode, just to make sure that you run some fuel through it so that it gets all the air out of the system. But
So you won't lose prime.
we won't typically lose prime, and even when we introduce fuel into the engine, you know, from the get-go, it's not often that we need to actually prime the system, because the gravity feed is usually enough to where it can draw fuel into the engine without having to do an external priming pump operation. Now, the fuel filter on the engine itself, the one that's attached to the front, actually has a lift pump to it. So it'll actually help the prime as well. If you were to draw fuel from the bottom of the engine, which is what most gen sets might do, that lift pump would help that situation and keep it primed. So it's really more of a backup priming system that is on that engine. But with the raised A tank, there's not a whole lot of priming that you have to do external, even when you're changing filters or having to drain the system for whatever reason. But yeah, I wouldn't just change a filter and just leave it at that without running the engine at idle, just to make sure all that air, if there's in it, any in the line, to get it out of there. So the fuel cooler takes the command from our PLC. It only runs when the engine's running. Okay, so when the engine is running, the fuel cooler receives a command to go ahead and run to cool the oil or the fuel oil that comes back through it from the engine itself. The day tank has a number of floats within it that control the filling of the day tank. The day tank comes with a fuel control panel that is its own self-contained way of controlling the fill of the day tank itself. So via various floats, via a high control float and a low control float, the tank itself will call for fuel from your bulk storage. Okay, so there is basically, there's a line coming into the tanks through some valves that call for fuel from your bulk storage, or there are actually some solenoid valves that will open and pressurize your system when the tank is calling for fuel. And that's all controlled by the tank itself and its own fuel control panel. The only interaction the tank has with our PLC is, again, to control the fuel cooler and also to give us alarms when we hit a low level or critical low, or we see some sort of a leak detect in the interstitial space of the day tank itself. Also, if the level of the day tank gets to what we call a critical high level, it will actually turn on a return pump, and it'll start pumping fuel from the day tank back into your main storage.
Are there any sight latches on the tank?
There is a gauge on the top of the tank that indicates its level. It's a little problematic because it's on the very top of the tank, and to see it, you have to get on a ladder. However, there is a secondary gauge on the fuel control panel itself, but it is not wired in. It requires 24-volt DC to operate. So we're going to provide you with a modification power supply that we're going to put in there that will enable that gauge to work as well. But right now it's not working. The only way is to look on top of the tank. It's one of our action items held over from last week. So again, low level alarms we get from the tank, high level alarms we get from the tank. Critical high will start a return pump, and we'll start returning fuel from the day tank back into the main tank. We have 2 sets of valves that will open to receive fuel from your bulk tank, and we also have 2 sets of valves for emergency stop, for emergency shut off. Again, if we get that high level indication, we're going to tell those valves to close and start pumping fuel back out into your main tank. There is a 3rd emergency overflow. Should everything else fail, then the overflow will enter the 3rd overflow line, and in theory that should go back to your main tank, but right now it's just being entered into the interstitial space, the way that is currently plumbed. And then you've got your normal vents, which are vented outside the building. We've got isolation valves, obviously, at various places. Make sure that those valves stay open, particularly the ones that are feeding the engine and in the return line. We actually ran the engine at one time with this valve closed, and we blew a line. So it's very important. And what I'd recommend on these isolation valves is that you put little signs on them that would indicate whether they're open or closed, because that's a little confusing at times.
Those are all manual?
Those are manual valves. Those are hand-turn valves. And I'll point those out to you in the walk around. Okay, let's look at the radiator or the cooling system. We've got to cool the engine, obviously, when it's running, and we do that with a remote radiator, which actually sits on the roof of the building. So there's 2 sets of piping that you'll see from the engine that will extend all the way to the roof, to the radiators. The radiator itself is a dual core radiator, because the engine is a dual circuit engine. There's a high temp circuit and a low temp circuit. Sometimes the high temp is called jacket water, and the low temp is called the intercooler circuit or AC circuit. But you'll have 2 sets of pipes, supply and return, coming from the engine, going to the radiator, either the high temp or low temp core, and then coming back into the radiator. So while the engine is running, there's a constant flow of cooling to the radiator for both circuits. The flow, of course, is driven by the water pumps on the engine itself. So the water pumps for the coolant on the engine will drive the water up into the radiators and back. Radiator has a fan motor, which is controlled by the Hitec PLC. So again, when the radiator is running, we give a command for the motor to engage the radiator fan so that it can cool the engine. The radiator also has an expansion tank for makeup, which also is piped into the engine. We actually pipe the fill lines from the expansion tank not into the core itself, but into the radiator right ahead of the fuel pumps or cooling pumps. Reason for that is we want to maintain positive pressure at the pump, and that helps prevent cavitation and wearing of your water pumps. And then of course we have regular vent lines from the engine all the way into the airspace of the expansion tank, and then we've got some vents from the cores into the expansion tank as well. The expansion tank has a sight glass where you can basically visually verify the level of the water in the expansion tank. We also have a float switch that can give an alarm to our PLC when the level of the expansion tank gets too low, for whatever reason. And then of course there are a number of isolation valves between the engine and the radiator, both at the radiator and near the engine as well, for isolation for whatever reason. Okay, it's actually nice to have those, because if you have to, let's say, replace a water pump or something on the engine, you don't have to drain the whole entire system. You can just close the valve and just drain part of the system in order to conduct whatever repair that would be. But again, a very simple system. It's a one-speed fan. It's either on or off, and the engine itself will actually regulate its own temperature with its thermostats. So it'll open the thermostats as much as it needs to regulate its own temperature, but the fan runs at one speed, and again, is controlled by the Hitec PLC. Okay. Other than the fuel system and the cooling system, the only other auxiliaries for the system are the exhaust system, which is just a very basic silencer with exhaust piping all the way up through the roof. And then, of course, I mentioned we have some ventilation fans that we provide power to. Those fans basically have their own controls. What we do provide the fan is two signals. We provide the fans with either a unit running signal or a diesel running signal, and then the fans will use those two signals to regulate, their operation, their speeds. They may also be thermostat driven as well. But all we do is basically tell the fans if the unit's running or if the diesel's running, and then the fans are programmed through their own controls to operate however they need to maintain airflow over the engine.
They're VFDs or?
That's a question for Stanley. I don't know the actual. Yeah, I don't know where their control panels are or if they're VFD driven. Again, fans weren't our scope. We just give them the signals that they needed to run. There is also a room temperature input that we take from a thermostat, so that we can alarm if the room temperature gets too high. Right now we are getting that alarm, and that's because the thermostat is set too low. So at some point, McKinstry is going to have to go in and raise that threshold because it's alarming at a much lower temperature than it should be. Which I'm not even sure what it's set at, because there's a quality assurance sticker that covers the setting of the thermostat, so we didn't want to touch that. But it needs to be set higher to get rid of that alarm. Okay, so that's why you saw the high room temp alarm on the UCP.